Okay, welcome to the first installment of guide sheet number 3. We're looking at the methods of charging. Really what we're trying to do is practice tracking the electrons as they move from one object to another and make sure we can understand how they move. Even though we can't see them, we want to be able to imagine what's going on. The guiding concept here is the law of conservation of charge. Just like our other conservation laws, the total charge of a system must stay constant. Now that doesn't mean the total charge on the individual objects in a system has to stay constant, but the total charge of all of the objects together must stay constant. So if I took 100 electrons from item A and put them on item B would now have an excess of 100 electrons, but that means item A would have a deficiency of 100 electrons. So item B would be overall negatively charged, and item A would be overall positively charged. So we got it to be the item A to be positively charged not by adding protons, but by removing electrons. Okay, so the electrons are the negatively charged particles in the atom. Each one has a fundamental charge of negative 1.6 times 10 to the minus 19th coulombs. Protons are the positively charged. Taking the pro side of an argument, you're taking the positive side. The protons reside in the nucleus and therefore cannot be removed or changed. They're tightly bound. The electrons are located outside the nucleus in the electron cloud, so they can be possibly moved around. In a conductor, it'll be easy to move them. In an insulator, it will be more difficult. As an object begins to gain or lose electrons from its atoms, again, it's only the electrons that actually removed, it becomes positively or negatively charged. A negatively charged object will have more of the negative charges, the electrons, than protons. If it's a single item, we'd call that an ion. A positively charged object would have more protons than it does electrons. And that's because we've removed electrons, not added protons. Okay, so we rub a plastic strip with some cotton, and the plastic strip became positively charged. The correct explanation would be that we had to, in order to get the plastic strip positively charged, we had to take electrons away from it. So nothing can acquire extra protons. Protons can't be created. It's always the loss of electrons. Now that means the cotton would have become negatively charged because the total amount of charge between the two had to stay the same. In the lab stations, we talked about charging by triboelectric means. That just means using the force of friction to take electrons from one item to another. Some items that you might commonly find are listed here in the triboelectric series. Now, that's a listing in order of their relative attraction of electrons. So near the top, those items have a strong affinity for electrons, and then the ones toward the bottom don't. So the ones on the bottom tend to lose electrons, the ones on the top tend to gain electrons. So if it gains electrons, it's going to end up with a negative charge, and if it loses them, it's going to end up with a positive charge. So these objects will tend to lose on the low end and thus become positively charged. These objects will tend to gain and therefore become negatively charged. And it's just a series, so you can compare any two. If I compare wood with silk, if I rub the silk on the wood, the electrons are going to move from the silk to the wood. If I compare glass and amber, they're going to move from the glass to the amber. Alright, so 4, when you pull cotton sweater off your skin, electrons are going to be transferred from. So human skin is below cotton, so they're going to move from the human skin to the cotton. As a result, your body acquires a positive charge because you're leaving behind extra protons, and the cotton will become negatively charged. If you rub a glass rod with silk, so the glass is down here, and the silk is up here, so the electrons are going to move from the glass to the silk. So from the glass to the silk. So the glass is going to end up being positively charged, and the silk will be negatively charged. If you rub a rubber rod with silk and then a second rubber rod with wool, the silk cloth will acquire. So rubber and silk, rubber's toward the top. It's got a good affinity, likes to hang onto electrons. Silk is down here, so the silk cloth will acquire an overall positive charge, and the wool sweater, which is rubbed with the rubber rod, wool's down here, so electrons are going to go from the wool to the rubber, is going to acquire a negative charge. Okay, since they're going to end up being opposite charges, they will then, in nature, opposites attract, so they will attract each other. Coulomb's law would allow us to calculate the value. If we rub glass with silk, then we know it's going to go from the glass to the silk, so the glass is going to be positive, the silk is going to be negative. And then the glass with the fur, it's going to go from the fur to the glass rod, so positive, negative. So the silk cloth becomes positive, and the rabbit fur will become also positive. So if we bring them, and that's a different glass rod that became negative up there, be careful about that. The rabbit fur and the silk cloth will then be observed to attract, because they're going to be opposite charges, and opposites attract. So typically when you rub any two things together using triboelectric means, one gains electron, one loses electrons. That means one's going to become positive, one's going to become negative. That means they're always going to tend to try to get back together and redistribute those electrons, so they will tend to stick. If you then interact them with other things, then you can change again. And these are all simply empirical measurements, comparing different items to see which ones have a stronger electron affinity and therefore are more likely to acquire than lose. Okay, saran wrap has larger electron affinity than nylon. If nylon is rubbed against saran wrap, then the electrons are going to tend to go to the one with larger electron affinity, so they're going to end up with the electrons going toward the saran wrap. So, and again, the electrons will always move in the direction of the higher affinity. So affinity, if I have an affinity for something, I like it. So objects with a higher affinity like to have the electrons. 9, a teacher rubs glass object with a felt cloth together and the glass becomes positively charged. Okay, so the glass gain protons can't possibly be true. The glass became positively charged, therefore the felt must have become negatively charged because of conservation of charge. Charge is created, charge is never created, it's simply transferred from one to the other. If the glass acquired a charge of +5, then the felt acquires a charge of -5. That's true. They're going to have to be equal in size but opposite in value. This event violates the law of conservation of charge. No, it does not. Electrons are transferred from the glass to the felt. If they were transferred from the glass to the felt would become negative, leaving the glass would be positive, so that sounds good. Oh, but then it says protons are transferred, so no, that can't be positive. True. Once charged this manner, the glass object and the felt cloth should attract each other. That is true. Anytime you rub one thing on another, afterwards they should try to rebalance. And in general, glass materials have a greater affinity for electrons than felt materials. In general, glass tends to have a very low affinity for electrons, whereas most other things tend to have a higher affinity. In this case, the electrons went from the glass to the felt, so the glass actually has a smaller affinity, so that's not true. So it's B, D, and G. Okay, that's it for just a triboelectric, charging by triboelectric means, which just means friction, actually using the force to rip electrons from one item to another, and that's how the electrons, how we decide which way they are going to move.